I share the screen and I'm gonna look at this. Okay, and let me see about starting here. All right, what I want to do is I want to look at load balancing. Load balancing is an incredible service that is available on cloud. It's not the only place that it's available, but it's one of the things that has made cloud a service that has a lot of appeal to many applications, many types of architectures. So what do we get with load balancing? What I want to do today is I want to just get you up to speed on what load balancing is in theory. So what is it? Why do we use it? What is difficult about it? All the different ways you can do it, so that you get an appreciation for what they've done with cloud and what they're offering you with cloud. So really all load balancing is that you want to have a methodology so that you can distribute work, right, whether it's network work coming in or application traffic or anything, across multiple servers. And so the idea with this is that you are going to want to have your multiple servers set up, and you want to say, as things come in, I want to spread them out so that it's efficient. So in other words, each of the servers does not have too much on it. And so we want to get the minimum response time and the maximum throughput for each of the resources that we have on the system. This also may include creating new resources. So load balancing in the theoretical sense that I'm going to look at here is the notion that you have X number of resources and you want to spread your load over those X number of resources. You also have the notion that you may create or delete resources so that you only have the resources that you actually need to maintain some sort of minimum performance. So a load balancer, therefore, is going to distribute traffic or requests for services or whatever to different servers in a pool of servers, and that pool may have to add resources to it to ensure that no single server becomes overworked. And if they become overworked, you also have the chance that it could become unreliable or unresponsive, or the application itself that's on those servers may become unreliable because it is expecting a certain response rate. So with load balancing, the idea is how can we achieve this given that we have certain resources? That also means, can we increase or decrease those resources? Now, we've got different algorithms to do load balancing. And before we get into this, I want to tell you why there's different ones. And the reason why is the amount of information you need to do the load balancing. So remember, the idea behind load balancing is that you want the best performance that you can get of the system. So that usually means fast response time, systems not overwhelmed so that the compute time can be as minimal as possible, like can work as fast as possible. You want to be able to get the response back to the user as fast as possible. But to do this, you're going to need to know information. And depending on what information you know or can get, then you have to choose different algorithms. And so we're going to look at 6 types of algorithms that are used for load balancing. These are the basic ones. So we have round robin. This is the simplest. This is the first one. This is the simplest technique. And this is where you have a system. So whatever is doing the load balancing, usually it's a server itself, or usually a smaller resource. So the load balancer is going to get all of the requests, and it's going to forward each of the client requests to a different server based on a rotating list. So if it has 3 servers, like we're seeing in this diagram, then it's just going to go based on this rotating list. So first it'll give it to 1, then 2, then 3, then back to 1. This is really easy to implement because it needs no information, well, almost no information. All it needs to know is how many servers it has that it can give out and which one was the last one that got it. So it just has a list, and it's basically just going through the list. It also is really going to treat everybody the same. So all requests are not obviously equal. So you may get a request that is going to actually take one of the servers a long time to do. And so that server is actually going to be a heavy load. And then there's going to be another server that gets the next request, and that request is really quick and easy to do. And so if we, like gave out a really heavy load to one, then a really quick light load to another one, another light load, and then we have the fourth request that comes in, it's going to go back to number one. Number one's still working away on that request it had before. So the upside to this is that it's really easy to do because you have to know only how many servers are out there. That's it, right? But you don't know what's happening with those servers. And so you save because you don't have to find out this information. But depending on what happens, it may not work so well. So you're really at the mercy of the requests that come in and how they come in, what order, what type of request. This also would probably only really work if they were all the same type of server. They all had the same capacity. That's the ideal way for round robin. Okay, now that obviously has a lot of flaws because you have all sorts of things. You don't know the load, you don't know anything about what's going on in the server. So now maybe what you'd like to do is try to get a little bit more information. So the least amount of information that you can get after nothing is called the least connection method. And with that, it's going to evaluate the number of connections to each of the servers. So it will have superior performance compared to round robin. And what it wants to do is it's basically, it's trying to save you from this thing there where one server got a very heavy load with the request that went to it was going to take a long time and take up a lot of resources. You don't want to go back to that server again. So in the least connection method, it's going to see that that guy isn't finishing the requests that it's getting. So the server that has a lot of active connections isn't going to get the next request. It's not going to get the next job. So it's going to, this is one way of seeing estimating load. So it's estimating load by the fact that the previous requests had not been satisfied yet, so there's still open connections, and it won't go to those. It'll skip that. So if one has this really weighty transaction, or in this diagram, it's actually number 2, it has 15 active transactions, you're not going to give it anything more because it's just got too much going on. And so now it's still not looking at how each one of those is weighted, like whether they're very heavy requests or not, but they're saying it's got a lot and it's not getting rid of them. So it must be busy. And so we're going to go on to something that has less connections. Now, this one is not too bad because the load balancer, it's easy for the load balancer to figure this out because it's keeping track of what's going on between the requests and the answer going back, the response. So because it's doing this, it can actually keep that count pretty easily. So it's not really something that costs a lot to implement. So for something that didn't cost very much, you get bang for your buck because you go from having no information in which to judge who gets the next request to having the minimal amount of information you already had, and it gives you an increase in efficiency. Now, another thing that you can do is actually try to find out what's going on with the server. There is there's 2 things that you could think about here. One, you may get a request that takes a lot of resources, it's a very heavy load, and the computing resource is getting slowed down with that. But there's also the possibility that that machine is having a problem. right? So maybe there's something else going on there, or maybe something that that request asked for has caused a problem. And so that machine's health could actually not be very good. So the next method for load balancing, it's called least response time method. So with this, it's going to look at the time taken by the server to respond to a health monitoring request. So in other words, this is an additional thing that the load balancer is going to send to each of the servers, and it's going to send out a request. It's just basically pinging it to say, how are you doing? And then it measures how long it takes to get an answer back. And so what that's going to do is it's going to say that's an indication of how loaded the server is, because it took some time for it to respond to this health request from the load balancer. So not only will it have the number of active connections, because it already had that anyway, so why not take that into account? It will also have this timing differential when it sends out a request. So it's more sophisticated than the last method. And so it's taking more things into account. So if we look at this, now what can the load balancer look at? So for each of the servers that it has, or the services that it has, if you look at in this diagram, you can see that you have 3 of them there. And it knows the active transactions, so how many connections are still active. It also has this timing, so time to first byte. So in other words, this is the response to the health monitoring message. And so it can actually look at then what does it think the least heavily loaded node is. And so it'll use those pieces of information. You also see here, it talks about weight. You can actually look at that as saying it might actually have an idea of what kind of machine, what kind of server is there, how weighty it is, how many resources it has. So it can take that into account, because it had that, once again, it was information that could be gotten right on startup for the algorithm. So if it has all of that information, now we're adding more and more and more information for the load balancer to make its decision about where the next request goes. So with least response time, it's going to go by this ping that gives out to see the health, how busy that server is. If it's really busy, it's going to be slow. And so it can do that. It can add to that the number of transactions it has, the size of machine, and it can figure out where it should go next. Least bandwidth is another one. This is really just another way of measuring a perceived load on the system. So it could look at the least amount of traffic that's going on between the outside world and the server, so it can measure that. But once again, it's like any of these, it's now having to gather information. So the other thing about this is how slow is the load balancer going to be? So, as it has to go out and get all this information, it's slowing down. So if it gets a request in and it has to do this idea of going out and getting information from each one of the servers, that's not cost free. And that's why the first algorithm started out with absolutely no information, because it's like, what can you do by just saying, I know I've got these servers out there, I'm just going to just parcel them out there without anything. And then they slowly built up into how can I get information that costs me very little to get? And so obviously they went through all sorts of things. And as things got easier to do or faster to do, or it wasn't going to cost the load balancer very much, they came up with other methods. And so you've got something similar is the least packets method. And this is looking to select the service that has received the fewest packets in a given time period. So once again, all of these are indirect measures of the system's load. So in all of these, it's not directly asking the system for its load or trying to calculate anything out there, because it doesn't really want to bother the system. So it wants just ping out there and ask for some information. And even if it was asking the system, that's still a complicated thing for the system to figure out in a reasonable time frame and in a reasonable way that gives a lot of information. And so the idea behind load balancers is to try to be very quick and efficient with the amount of information you gather so that you can make decisions that probably will give you, will allow you to spread out the load over all of the resources that you have. There's another one, and this is hashing methods. And in this category of load balancers, a little bit different. The decisions are made on a hash of various data coming, that is various data that you get from the incoming packet. And so the information may have all sorts of different information in it. Where it's coming from, where it's going to, the port it's going to, all this sort of thing, because a lot of these requests are going to come in through something like HTTP or whatever. So this may be an application, maybe it's a web application that's sitting on this service, and it's getting all this information in. One of the things that you might want to know is exactly where it's going back out to as well, not just what is going to happen at the server end. So hashes they're short and they're easy to use, and then the information that they're based on. But they still have enough information so that you can get this unique information packet to all of the different, to know which server you should get or which service you could get to handle the request. So you're just basically having ways that you can grab information, that you can do it, and you could, I mean, in this, you might be just sending the information off to all of them, and they may be choosing which one is the best one. Particularly, and you'll see this, I'm sure people that looked at edge computing, this comes up where the load may be going to the place where it's not the least amount is going on, but it's the closest to the request. So you have all sorts of different things to consider in this. You can also have custom load methods. So with this, this is the one where you're going to get the most information. And so this is the one that's going to take the most time for the load balancer to actually gather all the information. But with this, it's going to query the load on individual servers. And it's going to use usually SNMP, which is Simple Network Management Protocol. So this is a protocol for collecting and organizing information about managed devices on IP networks. This is usually what's used to go out and query the individual services and say what's happening. So the server load that can come back, and remember, because server load is complex. So the things that come back could be the CPU usage, memory usage, response times to various things, or all sorts of different combinations of all of the above. And so then what you have is a monitor, which is known as a load monitor, that calculates the load on each of the services in the system. So it's basically gathering all this information through SNMP, taking all that information and then calculating load. Right? So it may be taking into account all this different information that it was getting. So the monitor will make all these requests. So it'll ask for things, it'll get it back, and then it will figure out what it's going to do. So maybe it's going to be looking at the memory that's in use, because maybe it knows that the request coming in is going to need a lot of memory. Therefore, if you could go to a system that had a lot available, that might be a better solution than letting it swap itself to death. So it actually might, or you might want to go to somewhere that has large memory caches if you have different architectures on the end of for the different servers. And so it has this monitor. It's going to make all of these requests for information and then calculate out which one to send it to. So with this one, it really is the notion that you get the information that you need, and it can be targeted to the type of request coming in. So if it's got information from the request about what it needs, then it can go query what's at the end of all of its connections and say, okay, what do you have? You know, give me this information, and then it uses that to distribute the load. So we have all of these different methods. They can be used in combination. They can be used in all sorts of different ways. There's all sorts of customization that's possible, particularly given various architectures, network structures, nature of the different requests coming in. because this will depend on what it is that your what the requested work is. So you're doing assignment 3 on serverless functions. That's going to be a different load profile than if you're doing, if you have a web app out there that you want to have lots of people connecting to. So how does it, what happens in the cloud? Okay, so this is a major activity in the cloud, and one that people actually look to see if what they can do in the cloud is something that is going to be economical and efficient for them. So in the cloud, you want to redistribute your workload so that no computing resource is either overloaded or underloaded or idle. So this is a little bit, we've added this other thing in here. The first notion of load balancing, most of the time, the resources were static. So in other words, you had only so many servers that you were distributing work to. Well, that's not what happens in the cloud. I mean, obviously, yes, there is a physical limit to the number of servers you actually have, physical servers you have, and the number of VMs that you can spawn on all of them. But the fact is that when you are managing what your system is on the cloud platform, you can change the number of resources you have. And it's just as important to you to make sure that the resources aren't underutilized, because you're paying for them even though you're not using them. So, and this is why also you need to know what the requests are, because things that are pay per use, like serverless functions, it's a little bit different than for VMs, where, like, let's say a web app that needs a VM running, because that one is being charged whether it's being used or not. So we have to look at overloaded, underloaded, or idle. So we want, with load balancing, to speed up various things like response time, execution time, stability. We want to improve performance. And we want to usually improve performance in all of those dimensions. I mean, obviously you can't. Optimization like this, because this is an optimization task, is an NP hard problem. So mathematically, this is not an easy problem to figure out. And remember, in the cloud, we don't have just one instance of this. We have multiple instances of this. So it's doing it itself for its own resources, but it's also doing it for you. So you can do load balancing in the cloud at 2 different levels. You can look at the physical machine level or the VM level. So with the VM, it's in an overloaded state if its resources get exhausted, and it can't handle anything else. And so then you might have to migrate tasks to another VM. So in other words, you're saying, now I need another VM, all right? So this is different than physical, where you're dealing with a physical machine. Sometimes you can't say I need another machine. Maybe you have it, maybe you don't. But with a VM, most of the time you can create another VM. So, and usually you may be doing it on another machine, so it's even better. But then you would have to take tasks off one VM and put it on the other. So with migration, so workload migration happens a lot. So in those basic models of load balancing, they didn't talk much about what happens when you decide that one of the services or servers is overburdened. And so you want to take something and put it somewhere else that you have. They didn't really talk about that. It was just in how you were dishing it out. But there's the other one. Can they give it, can they give some of their tasks over to somebody else? So you have 3 steps. So there's load balancing. So you have to know the current load on a resource. There's resource discovery. So you have to find another suitable resource. So do you have another resource in your system that has capacity and ability to do that task? And then you actually have to move the task to the available resource. This is not easy. Remember, that task may have a whole bunch of things that it needs, and so it has to make sure that it has everything bundled up, or that all of those things are also at the other site. So you may have to do things like identifying the task requirements. So with this, you want to know the resource requirements of the tasks. So if you're going to schedule it for execution on a VM, what are all the things you need? So you need all the user tasks, you need the resource tasks. So you have to make sure that you know what the status of all the resources are on a particular VM. And so that way you get all the resource utilization going on a VM, and does it have unallocated resources? So with this, the status of the VM can determine where everything is going. So, at the very least, you have to know I'm overloaded. You have to know, another one has to know it's underloaded, right? And that that it can take something else. So then once the resource details of a VM are identified, the tasks are scheduled to those resources on that VM by an algorithm, by a scheduling algorithm. And the resources are allocated to the tasks for execution with a resource allocation policy. And so all of these things have to be there. So it's a huge optimization task to figure out how to do all of these things so that you can keep moving things around. So it's not only just when a request comes in, it's as things are running, you may have to move tasks around. So with the scheduling, this will speed up execution. You have to have an allocation policy so that you know you have proper resource management, and so that you know that when you do anything, you're going to improve the performance of the resources and for the tasks. And the load balancing algorithm has to do both of these things. So it has to have the allocation policy appropriate for the resources, and it has the scheduling that will speed up the execution of the tasks. So it needs everything. It needs those two to work together. So then migration happens, right? And so this is important because, once again, there's different ways of doing this, and they have different ramifications. So there's two types of migration. One is VM migration, and that's where you're moving a VM from one physical host to another one. And that way, the host itself may be what was running out of resources, so the VM needs more resources, so the VM itself is moved, right? Or maybe it needs a host that is larger, can do more things, so it's actually moved. And it can be done live or non-live. Task migration is the movement of tasks across VMs. And so you have the notion that you're moving the task, not the VM itself. Task migration is more time and cost effective than VM migration. And actually, in the cloud world, it's changed. Its load balancing used to be much more based on VM migration. So trying to, a VM that was getting overloaded was moved to a beefier physical environment, or a physical environment that didn't have too many VMs on it. And now they're actually looking at it as it's more efficient and effective to actually just move the tasks around themselves. And so that's what they've migrated to in the cloud world. So what's the benefit from doing this load balancing in the cloud? So this gives you scalability. So with the cloud, what you would like is that all of you have two things. You want, for your application on the cloud, you want it to be as efficient as possible, because then your performance will be good and it'll be what you need, and the cost will be as little as possible for you. From the cloud platform itself, it obviously wants to maximize the use of all of its resources. So it doesn't want, it has the problem of balancing what it's doing. It's not going to be very good if it doesn't balance, because then your task is going to slow down because of their problem with balancing. So the cloud wants to do it for a whole bunch of different reasons. So the real thing, though, is that you want to make sure that you can present a system alternative to people that are looking at going into the cloud, of this notion of scaling. And with all of this, what you want to do is, the cloud wants to do it itself. You want to do it yourself for your application, is that you don't want spikes. So we know that in all systems you have spikes. So sometimes it's a time of day, right? You know, so for the electrical system, it's when everybody came home from work, not now because everybody's still at home, but you know, when people came home, they would start making dinner, turn on the TV, and all of a sudden, all the, you know, the power shifted to be all this home use. So there's nothing during the day when people are off in their offices or at factories or whatever, but then they came home and they tended to come home all at the same time, and bang, they were doing that. People tend to do their washing all at the same time. So they gave you a break on electrical prices if you did it after 7 p.m. at night, because there was a spike in performance. So you have the same thing with requests to a computing resource. So you want to make sure that you don't get degraded performance when you have these traffic spikes. So everything's going to have traffic spikes. We see it every semester when they open up WebAdvisor so people can select courses. Nobody's been going to WebAdvisor for, you know, like weeks and weeks and weeks, and then all of a sudden, bang, everybody is going to it. And of course, you get degraded performance. You get degraded performance because they typically just have X number of servers, and that's it. And so there may be some load balancing, but it's limited. In the cloud, the idea is you're not limited to just those, you know, like 3 VMs that you have, or, you know, whatever. You can, you know, like normally you don't need, you need one because it's got very little traffic. And then it might zip up to 10, and then it'll come back down to, you know, 5, and then it'll go back down to 1 again. And so the idea is that it will do this auto scaling. And that's the other thing that you want in the cloud. Is one part of this is you need a monitor that's watching the traffic, and that you can then set up to say, if the traffic goes beyond a certain limit, because then you know performance will degrade, or maybe you put in something that looks at performance and says if it, you know, performance dips below something, now spawn another resource, right? And keep spawning resources to make sure that the response to the demand is smoothed out. So you don't want spikes. You want it being very smooth. And so you have the ability to put in more resources. You also have the ability to host the application in multiple places. So you can have various things. The load balancer can direct things away from a location that's having some particular problem. So sometimes you could have a network outage or some sort of event around the data center that will slow stuff down. And so you want to then move away from that and go to another place that's got much better response. And so you can do all of that within the cloud. And so what we're going to look at on Wednesday is we're going to just look at an example of how you would set something up on AWS to do load balancing. But the thing about this is that this is something to protect your application or your system against things that are often hard to control. And that is things like spikes. You can't make some of these spikes go away. There's nothing you can do to make people do things at certain times. You can, in fact, sometimes you have to make them all do it at a certain time and therefore contribute to the load balancing. You can't predict exactly when you're going to have a huge load on one part of the system because of outside things that are happening, maybe because there's some other resources that are going away because of a storm, or some backhoe has gone through a cable or something like that. You can't predict that. You can't protect yourself against that, except for the fact that you can move to another location, spawn up your resources there, scale up to what you need, and then come back down when you don't need it, so you don't have to pay for it. And just as a quick example, I was talking to one of our alumni, and his company was doing, it was a web app, and it was for the NHL, I think it was. Was it the NHL? Yeah, I think it was the NHL. Anyways, or Hockey Canada or something like that. But anyway, some hockey thing. And the day they launched was the day that they also announced the Olympic team. In men's hockey. And they had a huge number of people that suddenly swarmed to the site. And this was the day they opened the site. So they were having the big launch, and they had it in the cloud. Actually, they were using Azure, and they were really worried because they knew that the system was going to have to do this auto scaling to get this huge load, way bigger than they would anticipate for a normal day. And it worked. They actually didn't go down. They didn't have a performance that degraded to a point where it was unacceptable. And that was really good for their company, because that was a real, trial by fire, in that they had the worst possible thing happen, and they had set everything up so that they could actually handle that. So it is possible to do that. So what we're going to look at on Wednesday is, what are all the things you need to know if you were going to set this up on AWS. And it's very similar for the other systems, but we'll just look at AWS. So I'm going to end this now unless there's any questions. Do I have any specific questions about load balancing? I just want everybody to think about what a great resource this is, because as you've been seeing, that when you let something stay on your account for too long, you bleed all sorts of money out of there, or credits. That's what's happening when a company uses a cloud and they've got too many resources out there. So they want to use the minimum, but then you need performance. So this is a really important aspect from a application or business standpoint, is what you can achieve through cloud platforms that's very hard to do. You can do some of this yourself in an on-premise system, but it's difficult. You can do it, but it's difficult. So in cloud, it's a lot easier to do, because they've made it that way because they want you to use it. All right, so I think I'm not seeing any questions, so I'm going to leave it there.